everyone. Okay, so let's move on to chapter 11, the role of chance. Okay, so we've talked about probabilities in previous chapters. Now we're going to talk about how important chance is in effective research. It's really kind of counterintuitive how important the chance is in determining sound results, and how problematic it is to have systematic things that are operating in your experiment. So let's talk about chance a little bit, and hopefully that'll help to illustrate what I'm talking about. Okay, we talked before about how we have this sort of mistaken belief that everyone is unique, right? One size fits all, except for you, of course, because we're each unique. Everybody else might fit into this jacket, but I, of course, am the one special person who just doesn't fit into, off the rack clothes. Of course, we already have talked about the fact that everyone is not unique, but this belief makes us think that it's not a function of chance whether we have broad shoulders or narrow shoulders, or long arms or short arms, or a long torso or a short torso. We act like those aren't that those characteristics are not predictable through just the laws of chance. What I'm kind of alluding to here is actuarial prediction. Actuarial prediction is predictions that are based on past behavior. The best prediction of future behavior will come from past behavior. So if I know how you've acted in the past, my best chance for being accurate in predicting your future behavior will be to say that you'll just behave the same way that you have in the past. Now, sometimes I don't have access to knowledge of how you've acted in the past. Maybe you haven't had a situation or an opportunity to have acted in a similar situation to what's going to happen now. Now my next best thing to do would be to look at what other people like you have done in the past. Because average behavior is much more likely than outlying behavior. So I will be safer in my prediction if I suggest that you will probably behave like other people who share similar qualities to you have behaved in the past. So, for example, if I know that you're 20 years old, and I'm trying to predict your behavior in your first job or something, you've never had a job before. So I can't rely on your past behavior, but I can look to see how other 20-year-olds have behaved in their first jobs and assume that you're going to be like most 20-year-olds and behave in similar ways. Now, getting back to one of my favorite scientific topics to talk about, global warming, here we have a chart that shows in the blue line the instrumental record, that is the actual temperature readings from 1900 to, I think that's like 2012. And then we have the models that are in the red and the magenta and things like that. What I wanted you to notice is just in the blue line, notice how there are some high peaks and some low peaks that are below the smoother red line that's sort of overlapping the blue. I don't know if you can see my mouse. I can't see my mouse. There it is. So if we look at the blue, we see like some high points and some low points that are above the red line. The red line is the line of average. That's sort of going through and telling us what the average scores would be. We're going to be a lot more accurate if we go with these average scores, these smooth scores, than we are if we're going to suggest that any one individual behavior is one of these outliers. Those are unlikely behaviors. Those are unlikely outcomes. The smoother line is the likely outcome, and we should always go with the average. That's our best bet. Now in psychology, pretty much every field, every subtype of psychology describes average behavior rather than individual behavior. This can be really frustrating to sociology majors who think that it's really important to get individual stories from individual people in an effort to understand human behavior. For psychologists, we're a lot more interested in average behavior. Why is that? Well, because if I study an individual, that individual might not be representing very many people. They might be actually a minority of people. So here we have our little cartoon where the one guy's not wearing his Be Yourself t-shirt, and so they call him a nonconformist. He might be unusual. The average person is wearing a Be Yourself t-shirt, and here's this one guy over here with no shirt on at all. Which is a better set of data for us to focus on if our job as psychologists is to describe human behavior and mental processes? Well, we should probably look at the average human, not at the individual. So it could be that the individual's behavior is in the minority and not really useful for describing the average behavior. We also look at average behavior because when an individual becomes aware of what we're studying, they might actually change their behavior to avoid the predicted outcome. So our little cartoon shows him saying, wow, how'd you get him to work so hard? And she says, I told him if he didn't meet his deadline this month, I'd force him to install Vista on his machine. So knowing what the prediction is, this guy's working really hard to avoid that outcome. It's one of the things that makes psychology a really hard science to conduct, because we're studying humans, and they can discern what's going on and then alter their behavior to either help you and try and ensure that you get the outcome that you've predicted, or hurt you, trying to undermine the likelihood that you're going to be supported in your hypothesis. The thing about describing average behavior is that for each individual, we have a high probability of being wrong for an individual, right? I was just discussing with my personality theory class sex differences in traits. Traits include things like intelligence and stuff like that. And we can talk about average scores for women and average scores for men, but we can't talk about any individual and say, okay, I know that you're female, and I know that the average female does, this behavior, therefore you do this behavior. We can't say that. We're probably going to be wrong for an individual. But on average, for most people, we're going to be right more often than we are wrong. We have to accept the possibility of being wrong in order to reduce our overall likelihood of being wrong. So, if you recall way back at the very beginning of class, we talked about let's make a deal, the three-door problem. And we talked about how it illustrates some pretty fundamental issues about predictions and averages and probabilities, right? Well, there's a certain amount of chance involved in the three-door problem. I'm going to use an actuarial approach to try and maximize the likelihood that overall, in the long run, I will be right more often than I'm wrong. So first thing I'm going to do is test out the hypothesis that staying is the best strategy. That once I've picked a door, my best strategy is to stick with that door. So what I'm going to do is for 10 trials, I'm going to pick door number 1, and then no matter what the feedback is, I'm just going to stay with door number 1. So this is not going to be the most stimulating demonstration here as I just sit here and click. But I'm just going to keep going. So far I've lost one. I'm going to stay again, lost again, stay again. Ooh, I won, yay. Then I'm going to stay again. I lost again. You can see that it's accumulating my totals down at the bottom. Ooh, I won again. Yay, very rewarding. Okay, ooh, won again. Very rewarding. Okay, stay again. Oop, lost. Stay again, lost. Okay, so I've got 2 more to go. Lost again. Okay, so I won again. So I ended up with 4 correct and 6 incorrect with my staying strategy. Okay, now I'm going to change strategies. Now I'm going to try the switching strategy. And no matter what the feedback is, I'm always going to switch on when I'm given the option. So I'm going to start, just to keep everything steady. In good research, we keep as many variables steady as we can, and then change just the one that we think is important. So I'm going to start with door number 1, and now I'm going to make the change where I'm going to switch whenever I'm given the opportunity. So I'm going to, get my mouse to go. There we go. Ooh, I won. Yay. I've got to click on try again. Sorry. There we go. Click here to switch. Oh, I won again. Yay. Click here to switch. Oh, I won again. Oh, I have a string of wins. This is very rewarding. Oh, I won again. Yay. Try again. Oh, I won again. Wow, this is quite a hot streak I'm on. Let's see what's going to happen here. Oh my gosh. It's definitely hot streak. Oh my gosh, I've gotten all of them right. Oh my gosh, this is abnormal. I've done this many times. Oh, I finally lost. Okay. One more trial to make it even. Holy cow, I won 9 out of the 10 trials. Okay. Now, like I said, in this setup, I decided, regardless of feedback, I was going to stay for 10 trials and then I was going to switch for 10 trials. So I was trying to maximize my chance of being correct in the long run by switching for 10 trials or staying for 10 trials. And we have objective evidence that if everything else is being held steady, it looks like switching is a better strategy. Now, of course, I have no idea what the randomization policy is on this program, and it's possible that, starting by door number 1 did something to make the switches a better strategy or something like that. But that's really not the point. The point is that I had to accept certain times being wrong in order to, over the long run, maximize my chances of being right. And that's really what chance is all about. You want to maximize your chances of being right while minimizing your chances of being wrong. That's how you reduce error. But why do we try to avoid all error? That's a really good question. In normal human functioning, we don't like to be wrong. And as scientists, a lot of times we try and control every single variable in the hopes that there's no chance their hypothesis would be unsupported. Why do we do that? Why do we try to avoid all error? So we don't like being wrong. We look for evidence that supports what we already believe and avoid evidence that could show us that we're wrong. And losing is really punishing. Being wrong is really punishing. So we try to avoid all error in an effort to give ourselves the impression that we're right and that we never really lose or come to the wrong conclusion. In order to actually be effective, we have to sometimes be wrong in order to, over the long run, be right more often than we are wrong. So for an individual's behavior, I may not be able to predict accurately for an individual what their score on a particular personality scale might be just because I know what sex they are. But overall, if I took an entire group of women, I could increase my likelihood of avoiding error by saying that I think on average this entire group score is probably somewhere around, and then provide the average for females. That'll increase my likelihood of avoiding error. Okay. I'm going to stop here because I'm going to carry over into the next lecture to finish up this. And there might be, I apologize, a certain redundancy in the next lecture, but I'm going to make sure that everything's covered and I'm being comprehensive. Okay, so I'll see you in the next lecture.